Hello, Black Raiders. How you doing? Here for another Earth and Space Science demonstration. As you learned in the last lesson, we're moving into how we discover what we call exoplanets, or planets that exist outside of our solar system, planets that are way past Pluto, and found in other areas of the universe. And how do we find planets that aren't just around stars that we know of as the sun, but other stars that we see in far off galaxies. So I'm going to do a little demonstration to show you how it is that we use light that comes from these distant stars to discover what we call these exoplanets. So what I have here is a lamp, okay, and this lamp is going to represent a far off star. We have our telescope pointing at a star. We're looking at the light that it's sending us. So here is that bright star that is sending us all of that light, okay, and we're picking it up with a telescope. And right now we're picking up 100% of that star's light. So if we look at these graphs here that I have drawn, okay, what we're going to be taking a look at is something called a transit light graph. So if you think of this as a star, we're receiving 100% of the star's light right now. It's not blocked by anything. There's nothing in the way. If I put my hand in the way, then I'm blocking a whole bunch of the light. But if I move my hand, you're receiving 100% of the light. And it's pretty constant, which is why we have a straight line on each of these graphs. Okay? But what happens if something does pass in front of that light? It blocks some of it. And we, as astronomers, can actually measure the amount of light that is blocked. And actually, there's a really neat app on your phone called Science Journal. And if it has a light meter, certain phones can actually measure the amount of light that you receive. So if you do have any kind of interest in measuring the amount of light that, like, a lamp produces or something, you can do that. All right? So let's just take a look at this. So the first object I have here is a large ball. And what I want you to be thinking of with these different sized balls that I have here is that they represent planets. Okay? And the way that we know planets move is in an orbital fashion, right? They go around a star, which means that if you are the telescope and this is the light, when the planet passes in front of the star, it's blocking a certain amount of light for a certain amount of time. And then it goes behind the star and it's not blocking any light. But then sometime later, it comes back. So when this planet goes through its year, right? So Earth has 1 year in which it goes around the sun. Planets have different lengths of years. They're not always 365. So this is moving around that star and blocking the light when it does that. So we as scientists can use that information. So if this is my large object, okay, and now let's take a look at a smaller object, okay? So think about the amount of light that the volleyball blocked versus this tennis ball. Which one is blocking more light? Would it be the volleyball or the tennis ball? Obviously, it's the volleyball, right? If I hold the volleyball here, it's blocking a lot more light than if I hold the tennis ball here. So, because of that, we can measure the size of a planet based on its brightness. So, meaning that if I were to draw every single time this volleyball passed in front of the star as a graph, okay? So let's picture like time in days, like, right? Maybe like every 10 days or so, this is passing in front of the star, which means that this is a really fast year. This planet would only have a 10-day year, okay? If it's a really large planet, it's going to be blocking more light. You would see a dip that goes down really far and then come back up as it comes back around, right? So this is now 100% of the light again, and as it passes in front, it's blocking that light. So based on how far those transit light graphs go down, you can tell the size of a planet. Okay, compare that to the small planet. Okay, if I look at the small planet, the tennis ball planet, it's not going to block as much as that light. It's going to have a much smaller dip compared to this planet. Okay? And then the medium planet, right, if I have a medium-sized ball here, it's going to be somewhere in between the two as it goes around. Okay? So that medium-sized planet is going to fall somewhere in between the size of those two planets. Okay? So that's one variable, which is brightness, and that can tell us the size of the planet. If you block more light, that means you're a bigger planet. If you block less light, that means that you are a smaller planet. All right? And the other variable we have here is time. How often is that planet getting around the star? So if I come back to my small planet for a second, let's say that this small planet is going around the star. It's so far away from the star, it takes a really long time for it to come back around and pass in front of the telescope, you, and the star. So it goes, whew, it passes through, but then it takes another, let's say, 500 days before this comes all the way back around and then passes through again. So if it's taking 500 days for it to pass, that means that these are going to be really spaced out. So the next time that this passes might not be until here. And then another time it passes is going to be off the graph, right? It's taking a really long time for it to pass. But let's say that the large planet, it's going really fast. It's really close to the star. So that means it's going to, every 10 days, like I said, it's going in front of that star, blocking the light. It's going super fast. That would indicate a lot more dips. We're seeing more frequent dips because it's happening so quickly. So you might get a transit graph that looks more like this than this because it's blocking the light more frequently. There's a year, 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 right? That time in between transits, the time in between these would be 1 year for that planet. Whatever that might be. It might be, 10 days. Versus this planet, which is going to have a much longer time period, right? So this planet's year is the equivalent of, let's say, 50 days. It's 5 times longer. Even though it's a smaller planet, it might take much longer for it to pass in front of the star. And then for the, that was the medium one. Sorry, that was the medium one. And then the small one might fall somewhere in between, right? So that might be a little bit different for the small planet. The small planet might take like 20 days. Something a little bit different, okay, to go in between. So this might have a length of a year, which is the equivalent of, let's call it 25 days. Right? A time span in between these. So to summarize, okay, when you're looking at transit light graphs, the things that you want to pay attention to is that a deeper brightness curve equals a larger planet. Okay. More frequent dips and by dips, I mean transits. It's another, the appropriate word, the correct word is transit, but sometimes we call them dips just for more common reasons. Okay, so more frequent dips equals a faster planet. Because think about it. When you have a short string and you're swinging something around, it goes really fast. If you have a long string, it takes much longer for it to go all the way around. Okay, so more frequent dips or transits is a faster orbit. Okay, and more frequent dips or more frequent transits means that you're closer to your star. Okay, so that's a quick little summary of transit light graphs. And I just want you to take a look at all that information and use that to answer the next few questions on the next couple of lessons, because it's going to be really important. I'll walk you through them in another video, but this is going to be the really important piece that you got to remember, is that brightness, and the deeper the brightness curve means that you have a larger planet because you're blocking more light, just like the volleyball in front of the lamp blocked more light. That when you have more frequent transits, the planet is moving faster because it's passing in front of you and the star itself more often. And finally, that more frequent transits also mean that you're closer to your star. That if you're traveling faster, you are closer to the star, in the same way that if you have a ball on a string and you're swinging it around your head, a shorter string means the ball is going to be traveling a lot faster, and a longer string means the ball is going to be traveling slower. All right. Thank you guys for watching the video, and I hope to see you sooner rather than later. Enjoy the nice weather that we've been having this week, and I hope to see you soon. Bye-bye.